Welcome back. Today we will talk about specific heat capacity, calorimetry, change of state, and latent heat. These concepts we'd like to learn about. Now, if we have a tumbler here and I put in some water in it, or any other substance for that matter, and put it under the continuous flame of gas or Bunsen burner, okay, where the amount of gas which is coming per minute per second is unchanged. Okay. So suppose I take 1 liter of water or 1 kilogram of water, heat it for some time, put in a temperature measuring instrument, that is thermometer, and suppose we started at 20 Celsius or 30 Celsius, and slowly and gradually what happens is that this liquid is warmed and the temperature rises, and let this temperature rise by an amount of 20 Celsius. Okay? Well, so some quantity of heat has been given to it, and as a result thereof, the water over here, the thermometer tells us that 20 degrees Celsius temperature change has taken place. Now we can do many variations over here. For example, I can put in double the amount of water here, and then we give the same amount of heat which we can calculate by using a time measurement device, and then we find that when the amount of water has been doubled, the rise in temperature is almost halved. Similarly, we can change the substance. Instead of water, we can take some cooking oil or something like that, and then again repeat the experiment. For rise of 20 degrees Celsius, we find that the amount of time for which the flame is growing here may become different. Okay. So this kind of an experiment, when we carry out, then we find that the quantity of heat to warm a given substance, it depends upon many factors. For example, it depends upon the mass of the substance, it depends upon the change in temperature delta T, and it also depends upon the nature of the substance. Nature means many things put together which we are not able to define, prescribe, so that we call the nature of the substance. Now we define heat capacity S as equal to the change in the amount of heat, that energy, heat energy, divided by the rise in temperature. Okay. Where delta Q is the amount of heat supplied and delta T is equal to T plus delta T, the final temperature minus the initial temperature, which is equal to delta T. Okay. Now we find that if equal amount of heat is added to equal masses of different substances, then the delta T is not the same. The delta T may also depend upon change from substance to substance. So how we define that? We try to find out a unique value for the amount of heat absorbed or rejected to change the temperature. Absorbed, temperature rises. Reject, the temperature falls. Okay. So every substance has a unique value. for amount of heat absorbed or rejected to change the temperature of its unit mass by delta T equal to 1 Kelvin or 1 degree Celsius. So now we are defining unit mass, specifying the thing, and a unit rise of temperature. Such an amount of heat required, delta Q, is called specific heat capacity. Specific heat capacity. And this specific heat capacity can be shown by the letter small s, and there is nothing more to be done except that this is small s is equal to capital S, which is defined there as the delta Q upon delta T. So it becomes 1 upon m delta Q upon delta T. Of course, while we are making this definition, then the matter changes state. For example, ice, water, vapor. Okay, three phases, which is solid, liquid and gas. So when we are defining this thing, there should not be any phase change. That is, we will define the specific heat capacity of ice and water and vapor separately. Okay. So that means the specific heat capacity, besides being under the constraint that no phase change is taking place, it also depends upon nature of the substance and slightly on the temperature. So this is one way of defining it. The other way is that we are going to tell you is molar heat capacity. So earlier we had the definition of the unique heat capacity per unit mass of the substance, and it is better to specify it further and change the unit mass to the molar mass, okay, and convert it into n moles that will exist. So we define heat capacity per mole, which is represented by the letter C, which is equal to nothing but the value of S divided by the number of moles in it. And S is equal to delta Q upon delta T, so we get 1 upon N into delta Q upon delta T. By the way, this delta is not so small as it used to be in many other deltas. Here the delta is only for a change, okay, it need not tend to 0, okay, unless you go of course for the differential calculus kind of a definition. And like the other things which we have defined earlier, this C also depends upon may change from temperature to temperature, and it may depend also on the nature of the substance, which encompasses many things which you are not able to define distinguishingly. Okay. Now, this is about solids and liquids, okay. But for gases, because the gases have a different behavior, what we can say that in the case of gases we add certain conditions. For example, two of the conditions that we define the value of the molar specific heat is, one is the constant pressure and the other is the constant volume. Okay. Cp and Cp, and Cp is always more than Cp. What could be the possible reason? Here also I have just listed a number of gases: helium, hydrogen, nitrogen, oxygen, monoatomic and diatomics, and of course carbon dioxide. Here we find that Cp is greater than Cv, 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 Cp is greater than Cv. It's very simple to understand that. Why is Cp greater than Cv? In the case of Cv, in this case, because the volume is kept constant, therefore there is no expansion of gas whatever by adding heat to the substance. When there is no expansion, there is no water. But in this case of constant pressure, the volume increases, and in doing so, additional amount of work has to be done. So, therefore Cp is greater than Cv, and Cp upon Cv is a ratio which we define and which we will use when the time comes. Well, by the way, for not the molar specific heat, for the specific heat small c, aluminium I define in all these values are in joules per kilogram per Kelvin. Okay. This is 900, 386, 127, the least for the metal called lead. Okay, lead has very specific properties. However, what we find is that among all the liquids and many other substances except for example liquid ammonia maybe, the specific heat is maximum in the case of water. Even in the case of ice it is 2000. Kerosene also has a high value, and that is why we use water in hot water bottles or bags. Also we use water as coolant in automobiles. Water takes more time because of its specific heat or specific heat capacity to heat up the same amount of water by a given difference of temperature. It takes more time, more energy. Even to cool that, it takes more time, more energy. So you can see that in the deserts, in the daytime, if there is a water body, what we call the oasis, or even at the seashores, the water is heated to less extent than the earth over there, and that is why cool breezes they blow from, they are flowing from the sea to the seashore. Also, it quickly the sand gains the temperature and it's very hot in the daytime in the deserts, but in the night time the cooling takes place and the weather becomes a bit pleasant even in those circumstances. The next topic we want to discuss briefly is what is called calorimetry. We know that if there is an isolated system, I have shown over here, an isolated system is defined as one in which there is no entry of energy and no exit of energy. Okay, so heat does not enter it and heat does not leave it. That means there is no change in the value of heat in this isolated system. Calorimetry, it deals with the measurement of heat. Okay, what happens? It deals in heat transfers. Suppose there are two bodies, I have just shown it like that. So these two bodies of two different substances, they are all isolated bodies. They are brought in contact, the two isolated bodies. Now they are brought in contact. The temperature of the first body is more than the temperature of the second body. So the heat flow takes place from higher temperature to lower temperature. Just like I told you, from higher voltage to lower voltage, from higher elevation point to lower elevation point in the case of flow of water. Okay, so that is the change in the value of a small g. If g is more at one point and less at another point, so and the height that is there, that determines it. Okay, so what happens that if we have this system isolated, okay, by means of heat insulating materials, mufflers, which we may use, which are bad conductors of heat, like your wood or glass wool, etc., etc. So what happens is that there is a heat transfer. When there is heat transfer, the heat transfer takes place for such a time that there is an equilibrium temperature, and the two temperatures become the same T. Okay. In that case, one may have more heat capacity than the other, but the temperature is same. So what happens? The transfer of heat stops, and that equilibrium temperature T is greater than T2 and T is smaller than T1, etc., etc. Now a calorimeter is a device, like I told you before, is a device which consists of a metallic vessel, usually made of copper, plus a stirrer, okay, and this is put inside a heat insulating material. The outer jacket is made of wood. We can use cork also, and through the cork we can enter thermometer. Okay, and then of course we can put in some hot body inside a cold mass of water and see as to how much it rises. Similar kinds of numerical problems are given to us. The key thing is that in calorimetry, heat lost is equal to heat gained, and then the amount of heat is calculated for different bodies. For the metallic vessel in the stirrer, for the bodies under consideration, whatever. Okay, so this is what is called calorimetry. This is a very interesting subject, and there are many sources of error and precautions in conducting those experiments. So they are taken care of, and we consider normally that there is no loss of heat due to radiation, etc. Okay, we'll talk about that in the next lecture. Now the next thing is what we are all aware of is the change of state. And the change of state is from solid to liquid or liquid to solid. This is called melting or fusion. Okay, at standard atmospheric pressure, there is a normal melting point. Else, if the atmospheric pressure is changed, then the melting point also changes. Okay, so melting point is a function of the pressure. You can see that the melting point in the plains of Ganges and in the Himalayan terrace, they are different. Okay, so when the pressure, naturally the pressure as you go up the sky, the pressure is reduced, and so the melting point also changes. This is the interesting read. Okay, liquid to gas, when the conversion takes place, it's called boiling or condensation, and a normal BP is defined, boiling point or condensation point is defined at standard aromatic pressure. This also depends on the atmospheric pressure. Okay, there is a third kind of a thing which occurs, and that is solids don't convert into the liquid, but directly they convert to gas. This is what is called sublimation. For example, what we call dry ice, which is nothing but solid carbon dioxide with iodine, and also we know that camphor, they all exhibit same kind of things. In the change of state, as I will discuss in the following, that once these points, the melting point or the boiling point are reached, then the solid and liquid phases coexist. They are together present at the same temperature. For example, in the case of water and the gas, 100 degrees Celsius or around that temperature, we find that they coexist. Liquid and gas, that is, solid to liquid is the fusion temperature of ice, okay, that is 0 Celsius or 273.15 Kelvin or around, okay, that because it depends upon the pressure. Similarly, liquid to gas, this boiling occurs, and both phases are present at the same temperature. Similarly, in the case of whenever the sublimation takes place, we find that these two coexist. One very interesting thing is, and I would like to exercise your capacity to know that there is a triple point, and the triple point where the three states, the solid, liquid and gas, they can coexist at that particular point. So it's a very interesting read, and I suggest that you read it from your textbooks. So, latent heat. Latent heat is a heat which is required when the change of state is taking place. This has a very simple definition, that the quantity of heat required to change the state of m kilograms of a substance from solid to liquid or liquid to gas, or conversely condensation from the gas to liquid or from liquid to solid form, okay, is defined as Q is equal to ml. Okay, so its unit is joules per kg. I have shown it here also. Now there are two kinds of latent heats. One is that of fusion, LF, and the other is of vaporization. Okay. For some of the substances which normally at the room temperature, this is in the liquid form, and this alcohol is also in the liquid form. Nitrogen and oxygen, the two gases have been shown, and they are liquefied, okay, at these two temperatures, -196 and -183. This temperature is higher than this temperature, so that if we keep on cooling air, then first of all we will get oxygen, and thereafter I will get nitrogen. But, okay, it's otherwise for getting the solid oxygen and solid nitrogen. Okay, you can see that in most of the cases, in all the cases almost, LF is smaller than LV. 1, 8.5 into 10 to the power of 5 the units joules per kilogram. 0.26 and 2.0. 0.14 and 2.1. Because here the exchange is taking place between ordered system, and here one of the system is disordered, highly disordered, and that is the gaseous form of nitrogen, oxygen, or the hydrogen oxide, which is water. Very interesting that the amount of heat which is required for 1 kilogram of water to ice to convert into water, water to convert into ice, that's 3.33 into 10 to the power of 5 joules per kilogram. But whereas when you convert water into for the boiling point, when the water is converted into what we call vapor, then the amount of heat required is almost 7 times the amount of heat which is required over here. Now, I just show you with the help of a heat energy temperature diagram for the case of our friend water. Okay. And of course, this is shown, this has to be defined. The pressure is 1 atmospheric pressure. So that particular atmospheric pressure, we find that first of all, there is the value keeps on changing here for the heat energy which is required to do that, and then there is a phase change when the ice converts into water, or conversely water converts into ice. Okay, so this is when the latent heat plays its role. Okay. Later on, you can see that the specific heats which we can obtain as a slope, the slopes are not the same. That means the specific heat over here for the water is different from the specific heat of the ice, and it's different from the specific heat of water vapor. So here you can see that it is substantial, 22.6 into 10 to the power of 5 joules per kilogram, and the heat energy which has to be given is quite much. Okay, so we have come to an end of what we were, and now in the next lecture we will be in heat transfer, that is conduction, convection, and radiation. So thank you very much for being with us, with me, and of course, I'm not a good boy, I will always keep on showing you this, asking you to question, and then I think that I will answer. Okay, I will. Thank you very much.